that, I'm going to hand it over to our session chair, Mitch Wood.
Should be good.
Good morning. So far, great discussions on all of the talks, and I hope to meet and chat with more of you, and hopefully you're finding new collaborators as part of this workshop. We're going to start our session with someone who probably doesn't need an introduction. Mike Klein has a number of contributions to the field that are too numerous to list. Some of those that I was struck by when I was reading his bio was that he's contributed to science in more than just papers. He's put out more than 150 students, postdocs, and others who find themselves in mostly academia, but industry and national labs as well. So the impact on science is beyond the papers for Mike. He's also a member of the National Academy of Sciences. He had a stint as the Dean of Science and Technology at Temple University, taking it to one of the premier research institutions in the world during his stand. With no further ado, Mike.
Thank you. Good morning, everybody. Challenging. The only other place on the planet I've given a talk at 8:30 a.m. is Atomic Energy of Canada. And then you had to drive 120 miles into the bush to get there in time to go through security and then give a talk at 8:30. So welcome. The history of computational science is inextricably linked to computers. And the foundations of the field were laid by mathematicians in the 1930s. Key event, 1931, Alan Turing went to university to read mathematics. Another seminal event, 1932, Claude Shannon went to University of Michigan to read mathematics and electrical engineering. He was 16 years old. Astonishing. He came from rural Michigan. Turing's career, I don't have time in the short window for the talk to go through, but probably most famous for the work he did as part of the team cracking Enigma code. But he wrote a paper soon after he graduated. He was still an undergraduate on the decision problem. And unbeknown to him, he was scooped in this by a mathematician at Princeton. I'll say a tiny bit about. We celebrated 100 years of Turing's birth in 2012. Just briefly, Turing, as you'll see up there, in his paper, said computable number is essentially one that can be expressed as a decimal in a machine. The paper that scooped him was by Alonzo Church at Princeton, founding editor of the Journal of Symbolic Logic, who published in the first issue of that journal his paper on effective calculability. So when Turing wrote up his paper, so after he graduated, he got a research fellowship at Cambridge. They're quite common. You often get 5 to 7 years to do what you want, go where you want. And he took a course on logic from a mathematician at Cambridge, Max Neumann, whose family had been refugees from Nazi Germany. His original name was Neumann, not von Neumann, and he anglicized it to Neumann, a famous character. And Turing gave him a copy of the paper. Unbeknown to him that Neumann knew Alonzo Church and knew Alonzo Church's papers, and he showed Turing this paper. And then I've highlighted in blue there what Neumann wrote to Church, that Neumann's paper caused a lot of distress for Turing. So the end of Turing's paper, he acknowledges Church's work. Not only that, he then went and did a PhD with Church at Princeton. And he did a PhD in less than 2 years. Claude Shannon was another genius that got out with his dual degree and then went to do a master's degree at MIT. His master's thesis was doing the mathematics, the logic of essentially printed circuits. This original work was presented at conferences and published in 1938. that thesis at MIT website has been downloaded over 100,000 times. Just to tell you, one could argue that this is the greatest master's thesis ever written. And this set out the whole logical way to do a circuit, and instead of doing it arbitrarily. And as he says in the paper there, he's using the calculus of propositions which come from symbolic logic. Just go back a minute to here. During the Second World War, he worked at Bell Labs on trying to encrypt, and it was the telephone company, and they were charged with trying to get Roosevelt and Churchill to be able to communicate secretly. And because of that work, it turned out that Turing was working on the Enigma code and so on in the UK. He was sent to the US for a couple of months, and he spent a lot of that time at Bell Labs, overlapped with Shannon. It would have been wonderful to be the fly on the wall. What did these guys talk about? I mean, they were both introverted nerds. Apparently they had tea every day. It would have, who knows what they spoke about, but they did stay connected. About 10 years later, just before Turing committed suicide, Shannon invited Turing to write a paper in an edited book he was doing. At that same time, a couple of engineers at the engineering school at UPenn embarked on building a computer. Actually, I think the title ENIAC was the last C, and it was actually calculator, I think, not computer. And this took 3 years to build. And because it was the wartime, they were kind of forced to hire as technical people female mathematicians. I actually learned about this when I read the obituary of Kay McNulty, who died in 2006. I was unaware of this until I read that obituary. This was an engineering marvel, weighed 30 tons, 5 million hand-soldered joints, and it worked, and was delivered to the US Army, Aberdeen, Maryland, about halfway between Philadelphia and Washington. The computers were the women, that actually there was no coding. You had to rewire the machine for every task. During the construction of this machine, the inventors, Presper Eckert and John Mauchly, they were already planning the next machine. And von Neumann muscled in on this because he wanted to have such a machine, the next generation, built at Institute of Advanced Studies. And he took it upon himself to write a report on this soon-to-be machine, which he went around publicizing. In my view, looking back at the history, kind of shamefully adopting what these guys have done. But he was a consultant to everybody, including IBM, and that's how IBM was able to keep abreast of what was going on, my interpretation. Anyway, von Neumann publicly said that Turing's machine was simple and neat, but didn't tell him how to build a computer. However, that never stopped von Neumann going around lecturing on Turing's machine. I managed to find copies of his lectures he gave every summer at UPenn in the 1940s about Turing's machine. Did I miss one? Yeah, so then we had the MANIAC computer, which took, again, another 3-year effort, but this was massively lighter. It wasn't 30 tons, it was half a ton, still pretty heavy, and was delivered to ENIAC. And that signifies the beginning of our field, basically. However, in parallel to this, what was going on was the commercial enterprise of trying to build commercial computers. And the first commercial computers were actually built in Philadelphia by Remington Rand Corporation. Interesting factoid, the person in charge of buying up the 2 existing private ventures at that time was the same guy in charge of building the bomb at Los Alamos, General Groves. And he was the one that brought these sort of rogue companies to fruition. story for another day and another time, particularly with a drink in your hand. Anyway, that brings us to the birth of really what I was talking about. And I was asked to focus on the 80s and 90s, but I can't avoid acknowledging these pioneers. And those of us in the early days of this field wondered who invented the algorithm and the Monte Carlo, because a group of people don't sit around and invent an algorithm. It has to come, the germ has to come from somebody. And it seems clear now that it was Ariana Rosenbluth, although for many years, if I even go back 40 years, Bernie Alder claimed that he invented Monte Carlo. And there was a meeting in Vienna in 1985 where a group of us, including Dan Frankel, challenged Bernie to explain to us what he actually did. And in fact, it wasn't important sampling. And anyway, he went to his grave believing he invented Monte Carlo, just randomly inserting something. Of course, in a dense system, that's a very improbable event. So anyway, but there's a footnote in the paper, which I think a lot of people ignore. It actually acknowledges talking to Bernie Alder and Stan Ulam. So maybe in his memory, Bernie imagined this talking to them, he was part of the invention. It's quite clear when you look at the literature, there are lesser known papers by Ariana and Marshall Rosenbluth, where they use this machine to do other things than what they're famous for. Bernie's claim to fame is real. I mean, his paper on molecular dynamics for hard sphere systems. I interacted with Bernie quite a lot in the 70s. Bernie wasn't interested in anything that didn't involve hard spheres. So in fact, that's probably why he missed his Nobel Prize, but he just was obsessed with hard spheres. Journal of Chemical Physics has just put out a list of 90 papers over the 90 years of the journal, and this paper of Bernie Alder Wainwright paper. You can find in the CCAM website links to talks and interviews of people involved, and encourage any of you interested in the history to go and check. And also the Frankel Baron Smith book has a chapter on the prehistory of computing, which is a good read. That brings us to the 60s, which is kind of my decade. I started research in the summer of 1960 for an undergraduate thesis. And the 60s brought us molecular dynamics of solids and liquids and the density functional theory of electronic structure, all things that underpin what we all do today. So as a graduate student, I was sent to a conference on lattice dynamics. And at that meeting, George Vineyard from Brookhaven National Lab showed a movie of radiation damage, channeling of energetic particles coming into a crystal. This paper, if you look it up, has the same algorithm that we often call the Verlet algorithm. And a few years back, Jean-Pierre Hansen and Dominique Levesque wrote a paper showing that the Verlet algorithm is exactly the same algorithm that Newton used to integrate planetary motions. So we should call it the Newton method, because that's what it really is. And way before Verlet, we have this paper from George Vineyard and his group that invented molecular dynamics. At that meeting that I went to as a graduate student, Ewald gave a talk where he said, it shouldn't be called the Ewald method. He said, we were all students of Max Born, and after lunch, the group went for a walk. And that was the only time the group could communicate with each other, because we all worked in one room at our desks. We had to be silent while Max Born had asleep at his desk. If we talked, we would wake him up. On one of these walks, I was explaining to Peter Debye that I was having trouble getting an asymptotic series of 1 over r to the n to converge. And all Debye said, think reciprocal space. So that was the story Ewald told in 1963. I met other people there. Soon after that, Anish Raman's paper, which in many respects, looking back, was more psychological than a massive achievement. He did have a system of 800 particles in a box, and he ran it on both an IBM 704 and a CDC 3600. 8 years later, I was using a 3600 Atomic Energy of Canada lab, still running, and it was the best machine in the whole country still at that point. Just a word about Seymour Cray and that machine. Cray was one of the group that left Engineering Research Associates in Minneapolis and joined, well, actually made the Control Data Corporation. And he was a designer of the 1604, the CDC 6600, and the other series, and also the 7600, which were big machines that some of us may have known about and even used. I mostly used this 3600 that was at Atomic Energy of Canada in the early days I was in Canada. The next summer I was lucky enough, I just finished my PhD, submitted it. I got an appointment at physics at Rutgers University, and my boss there, George Horton, sent me to a summer school on many-body theory at the Atomic Energy of Canada lab. It was held. They had a thriving theoretical group there. And I heard Walter Kohn lecture on Honeberg-Kohn theory. In the audience sitting beside me was Lou Sham, who just graduated the same year as me. And he was about to go off to be a postdoc with Walter Kohn. And that's history. Kohn-Sham orbitals came out of that with this massively popular paper. A couple of years later, I came back to the US for the summer to work again at Rutgers in the physics department, and I did a mini tour of the US visiting the national labs. And why were people interested for me to come here in 1966 and give a talk? Well, one of the chapters of my thesis was concerned with how you define the thermoelastic properties of materials under stress. Why was I interested in that? Well, my thesis project was about zero-point energy. And intuitively, when you think of an atom not as a point particle, but being puffed up because of zero-point energy or wave function, I thought, well, to understand what happens with the zero-point energy, I should first do the reverse. What happens when we compress something? So we can understand negative stress. It led me to spend several months going through the research literature on elasticity back to the pioneering work of Cauchy in French in the 1800s. And I wrote a chapter in my thesis, which was to summarize all this. My advisor, Hugh Barron, thought this would be of general interest. It got published, and I guess a couple of years later got discovered, and I was invited here to talk about materials under stress. It brings us to the age of the 6600, which was the fastest computer in the world for some period. I was talking to Gary. Did you get to use this? It was the fastest machine in the world in the 60s. Again, Seymour Cray designed machine. I'd already mentioned in the first machines, the 3600, that Seymour Cray believed that if you were going to sell a machine for millions of dollars, it should look special. So the 7600 had these glass panels, which would look like sapphire, and it had walnut trim on it. So you could add another few $1 million to the price tag. Fabulous machine. So end of the 60s, we started to think about molecules instead of atoms. That meant chemists got involved, not just physicists. And I moved to Canada in 1968 to put my first permanent job. And I connected with John Barker, who at the time was in applied math at the University of Waterloo. And John told me about the calculations he was doing on liquid water. This was the first publication of a simulation of a molecular liquid. Sadly ignored. It's totally ignored. It's been overrun by the subsequent work I'm going to talk about. So as we entered the 1970s and we wanted to study molecules, the real issue was, where do you find computers? So here the pioneering work was Frank Stillinger. He was at Bell Labs, and he tried connecting with the academic community to try and persuade people to model water, in particular Bruce Byrne, who all said, no, we don't have the computer time to give you. But Anise picked up the challenge, and then there are a couple of papers in the early 70s on water. And these papers are included in this collection of the significant papers in Journal of Chemical Physics. I don't have time to say very much at all about the move into biology and biophysics, but biochemistry, biophysics, but this was certainly stimulated by the modeling of water. Herman Berenson, behind the scenes, was the guy pushing a lot of this. He also pushed computation. The seminal paper for me was Peter Roski spent a couple of months in the summer of '76 at a CCAM workshop. Herman Berenson and company were there. He was working with Anis Rahman. At the same period, at the same time, I was actually on sabbatical at University of Paris. I was in the theoretical and high energy physics group. They had their own personal UNIVAC 1108. So all of my molecular dynamics calculations done in collaboration with Dominique Levesque and Jean-Pierre Hansen were all done using this UNIVAC 1108. It had a beautiful tape system where we could store our data and then go back and run time correlation functions and so on. Just a word about Peter, because there's a really strange factoid here. So as Peter, in his own words, in 1976, Karplus got in touch with Rahman and sent Andy McCammon and Peter to spend the summer at CCAM in Paris, working with Anis. And what came out of that was the CCAM report, which is published the following year, where there's a chapter in that by Peter Roski and Anis Rahman modeling a dipeptide in water. When the publication appeared in the American Chemical Society, it appears as Roski and Karplus, and Anis Rahman disappeared. I never got an explanation from Karplus as to how that happened, but anyway, he got his Nobel Prize. 70th brings us Cray. Seymour Cray, he got upset with the people at CDC that wouldn't sponsor his thing, so he moved on and created his own company and built the Cray 1. It was the 70s, so if you look at the clothes he's wearing, and that's why I colored it purple. 70s were different. So he managed to sell these machines for $9 million each. It was referred to as the $9 million love seat because of the place around it, which was for the cooling system. He believed to make fast machines, you had to make them smaller and more compact, and the challenge was to cool. And he had liquid freon passing through the system to cool it. A really novel idea. Can't leave the 70s without a shout for Shake, the beautiful paper on how to handle chain molecules instead of using torsional potentials, using holonomic constraints. This is a massively cited paper. And these guys, it was Jean-Paul Ricard's thesis, and Giovanni Ciccotti was around at CCAM at that time. And Herman Berenson was the driving force for getting this done. And Giovanni solved the problem, the mechanics problem of how you let the equations evolve and then you refix all the bonds. So that's Shake. If you go on the web, you can find a lecture by Jean-Paul and Giovanni, but I caution you, you have to learn Italian sign language if you're going to get anything out of this video, as you can imagine. Let's skip the 70s, the rest, because, you know, the 70s was special. So that brings us to the 80s, nostalgia. Do you remember, any of you remember these things? They lived a long time after the 80s, but it was different, right? I know that I wired my house with Apple Network, and I had 2 Apple computers in my house in the 80s. Actually, they were expensive compared to salary. That's one thing that's happened, right? We might think this phone is expensive, but compared to your salary, it's not. So just another couple of factoids. The first laser printer came out, it was $100,000. So that's gone down a factor of 1,000. And the gigabit hard drive, first of all, it weighed 3 times me, and it cost $40,000. So this has got 1,000 times cheaper for 1,000 times more memory. So we've gained a factor of 1 million just there. 1980, Michele Paranello decided to go and spend some time working with at Argonne National Lab with Anisur Rahman, and that changed the field, I would say. So that's the Reagan years. So finally, I'm into the 1980s, and lots of things happened. I can talk just about a few of them. Hans Andersen's paper was really important. He brought us the extended Lagrangian, how you could add extra variables into the dynamics. This was profound. In fact, when Hans retired from Stanford, I was asked to give the after-dinner speech. And I wrote to Michele Paranello, I said, Michele, can you give me a sentence or two about what I can say about that? And he said, this paper created my life in science, the extended Lagrangian. So, I mean, Michele is not famous for writing long things. That's what he said. So profound. He had profound influence. So the Gordon Conference that year on liquids, I was a speaker there, so was Anis. And you gather outside on the grass, and Anis came running across the grass, waving the Mike, look. This is what I've just done with Michele. You've got to do this for molecules. He'd done it for ionic solids and then other solids. If it had been easy, he would have already done it. So it took us a year and a half. I had to learn about quaternions, even focusing on rigid molecules. It was not so trivial. In the meantime, this seminal paper came out, the pair of them, and what they'd done. And then our papers came out on materials under pressure, watching it crystal. But we were focused there on small molecules. Shuichi Noze joined my group. He with Roger Impey, wrote the codes that did that. It was beautiful to be able to set up a system and let it find its own equilibrium. Shuichi spent 2 years with me. He published 12 papers. Incredibly brilliant, probably the most brilliant postdoc I ever had. It enabled me to do a collaboration with Bill Jorgensen. Roger Impey wrote a general code that had long-range forces and other things in it, and it enabled us to connect with Bill Jorgensen, who was doing constant pressure work, and of course we could run diffusion constants and other things. Really, this was the culmination 50 years later of the seminal paper, one of the 90 special chosen by JCP of Bernal and Fowler, pioneering paper. Shuichi came to my office one day with a couple of articles written on how he wanted to do canonical molecular dynamics. And I told him to take my name off the papers. I could never have dreamed of doing this. Okay. And these were incredible papers. And again, Shuichi Noze's paper was one of the ones selected for this special issue. A shout out to work done by Don Frenkel, constant pressure Monte Carlo, phase diagram of, he had in mind liquid crystals. And then in '84, we celebrated Anis because he was terminally ill with cancer. And we had a conference where we invited people. I was one of the organizers. And at this meeting, anybody who was anybody was there. Gary Gress was there. There's the proof. Martin Karplus was there. Michele Paranello was there. Charles Bennett was there. There's Gary again. There's me with Don Frenkel. And Michele Paranello was hiding in the back in this picture. There are lots of other luminaries there. 2 Nobel laureates in this picture. They were not Nobel laureates at the time. John Popel and John Polanyi. But there was another Nobel laureate that I showed you earlier, Martin Karplus. So 3 of the people at this meeting got Nobel Prizes. And I don't think we've seen the last. So those days were special. Internet wasn't really that powerful in the early 80s. Anis and I communicated on punch cards. Here's a picture of a punch card in my pocket. We would scribble notes, either put a postage stamp on the card and send it, or put it in an envelope and send it. And here's the proof. I work for the government, so my mail was opened. And you'll see here the timestamp received at the National Research Council. And when he wrote me a card, he just used to address it Mike Klein, Sussex Drive. Didn't he say the building? Didn't say the number? Obviously, the Secret Service knew who I was. I had many visitors from the Soviet Union during this time. So the Canadians knew who I was. The next year was Carl Paranello, changed the field. Can't resist showing another Cray. Remember I said Cray thought his machines should be arrestingly beautiful. This is the CERN Computer Center in the 80s. Shout out for this incredible decades of work by Gary and Kurt Kremer on polymer systems. Again, Gary's paper with Kurt chosen for the special issue. Important things happened in the 90s. My group contributed something in the field of algorithms. Both these papers are part of this special issue. We again came to graphics in the 90s, silicon graphics. Silicon graphics enabled us to render beautiful images. And the guy in my group that did that, the work was the last student of Anisur Rahman, who after this work became a successful commercial artist. He paints wildlife. So it happened to me one day, I got a phone call saying, I won't be coming to work today. This was Joe. I'm going to meet the president. I got to go buy a suit. So the president of what? The president. He just won a competition for the federal duck stamp. And he was the guy that made all these images in my lab. So he was good. But the guy who wrote the software was graduate student John Shelley that enabled us to render surfactant systems. We could also render electronic charge distributions. Here's a picture of a bipolaron in a polar solvent. We could watch the metal insulator transition by adding more electrolyte and see the electronic bands go all the way through the liquid. Beautiful things happened here. People were worried about getting great software. Shout out to Steve for this monumental work. Also in the 90s, we had John Padu's PBE paper, 220,000 citations. Probably when I get back to my lab, you're going to find this number's gone up as you look at it. Got a shout out for Seymour Cray. This year marks the 100th anniversary of his birth. I don't know that anybody's celebrating that. This guy changed the field completely. His name is synonymous with supercomputer. I'm going to skip through just quickly. We've got some great memories. I can't stop without saying I want to highlight this paper of Michele, which was stealth. Nobody paid any attention to it for at least 5 years, at least 5 years. It was just sitting there, unnoticed. Fabulous contribution. Now it has 5,000 citations. You guys have contributed phenomenally here. I'm thrilled to see you work with Gabor Chanyi, who is one of my heroes for what he's done in UK. I regard myself as a silent partner in LAMPS. I have not contributed anything other than emotional, maybe. I'm thrilled by the success. Here's a paper with 9,000 citations in just 2-3 years. This is amazing. Say hi to Axel. Hello, Axel. And last slide, if you go to the list of top 500, 4 of the top 5 have the name Cray associated with them. So when I gave a talk about Cray at Princeton recently, a couple of people came up to me and said, I didn't know that Cray was a person. I thought Cray was a computer. And there you go. Okay, I'm done.
Well, I'm more than happy to ruin the schedule after just one talk, because that was quite delightful to get a recap like that. If there's questions in the room, I can come give you a mic. If there's questions online, if someone could flag me, and we can repeat the question for Mike.
I'm sorry I went over. I just had a lot of ground to cover.
No trouble. 80 years is a summary of our field is a lot to cover.
Is this in a book anywhere? Like a history of this written down would be fantastic to work through.
So I have, if you go to Mike Klein YouTube, if you Google that, especially when I go to Asia, they seem to tape my talks and put them on YouTube. You'll find several. One is called The First 30 Years. And just Michael L. Klein YouTube, and you'll get more than you need.
Instagram, TikTok?
I don't do it. I mean, other people do. I lived it, so it isn't so difficult. You know, I knew Walter Cohn, and I was perhaps an unusual student. I was a chemist that when I entered chemistry was only doing the gas phase. But I knew chemistry of mixing liquids or putting solids in liquids. But everybody in the lab was worried about diatomic molecules in the gas phase because that's the only place quantum mechanics work. So I became a groupie in physics. Physicists weren't interested in liquids back then. They were interested in solids. So I thought, well, I can go from solids to liquids. And so I was blessed with the people who taught me at Bristol. Incredible characters. People that had overlapped with Leonard Jones, who's a person, not just the potential.
Mike, I have a technical but very broad question for you. Why do you think that when you look at these many decades of molecular simulation, at the start it was split 50-50 between molecular dynamics and Monte Carlo, and now it's dominated by molecular dynamics? Do you have an opinion about that?
Yeah, so Monte Carlo, looking back for us, was easiest to enter. In fact, after my contact with John Barker, he encouraged me to do I was interested in molecular crystals. So I did work on nitrogen and carbon dioxide. In fact, that paper of mine on carbon dioxide from way, way, way back has been rediscovered. Everybody's worried about carbon dioxide, but we got an intermolecular potential for carbon dioxide, not particularly good, but so it was easy to program. The only thing that some of us were obsessed with, how random should be the random number. So I spent a lot of time talking to it. And as they say, random numbers mainly fall in the plane, in the famous song. Okay, the rain. Anyway, in the end, it doesn't matter because it's statistical anyway. So that took us months, if not more than a year, to get over that. Should they really be random, or does it matter that they're correlated? So we use random numbers to pull random numbers, and I mean, it didn't matter. So that was the easiest to get into. The other issue was storage. Where are you going to put the data from your molecular dynamics? Because you want to do time correlation. Otherwise, what's the point? So as I showed that picture of the 1108 that had tapes. So it wasn't uncommon to do a trajectory that ran the whole weekend, right? We weren't allowed the time during the week, but had the whole weekend. You come in the morning and one of the tape drives failed. So you know, you've got to wait another week. So that was why early we did quantum Monte Carlo, we did quantum, it just was easier. If you kept the configuration, it was a box of cards.
Now we don't need easy anymore.
Right. It doesn't matter, right?
Yeah.
Yeah.
Okay, let's thank Mike one more time.